In 1998, two teams of astronomers made a discovery that shattered our understanding of reality. They expected to find the universe slowing down, pulled back by gravity's relentless tug. Instead, they found the opposite. Something invisible and powerful was pushing space itself apart, accelerating the expansion of everything we know. That something makes up 70% of existence, yet we have no idea what it is. This mysterious force earned the name dark energy, and it represents the most deep puzzle in modern physics. Albert Einstein called his prediction of such a force his greatest blunder. The three scientists who discovered it won the Nobel Prize in Physics in 2011. Yet nearly 3 decades later, dark energy remains completely unexplained. Quantum physics predicts it should be 10 to the 120th power times stronger than what we observe. Recent measurements in 2024 and 2025 have made the mystery even deeper, suggesting dark energy might be changing over time. If it strengthens, it could eventually tear apart every atom in the universe. We're living in a cosmos dominated by something we don't understand, and new evidence suggests it's not behaving the way we thought. The story begins with Einstein's mistake. In 1917, Albert Einstein believed the universe was static and eternal. His equations of general relativity suggested otherwise. They predicted the universe should either expand or contract. To force a static solution, Einstein added a mathematical term called the cosmological constant, a repulsive force that could balance gravity's pull. When Edwin Hubble discovered in the 1920s that galaxies were racing away from us, proving the universe was expanding, Einstein abandoned his cosmological constant and called it his greatest blunder. For 70 years, that seemed to be the end of the story. Astronomers expected cosmic expansion to gradually slow down as gravity pulled everything back together. The universe should behave like a ball thrown into the air, eventually slowing and falling back down. Two competing research teams set out to measure exactly how much the expansion was decelerating. The Supernova Cosmology project, led by Saul Perlmutter, and the High-Z Supernova Search Team, directed by Brian Schmidt and Adam Rees, both used the same approach. They would observe exploding stars called Type 1a supernovae as cosmic distance markers. These supernovae work as standard candles because they all reach nearly the same peak brightness before fading. Picture a cosmic lighthouse with a precisely calibrated bulb. A white dwarf star accumulates material from a companion until it reaches exactly 1.44 times the mass of our Sun. This is the Chandrasekhar limit. At that precise threshold, the white dwarf explodes in a thermonuclear blast that completely destroys it. The explosion releases the energy of 5 billion suns in just seconds. Since the explosion mechanism is nearly identical each time, these supernovae can be used to measure cosmic distances with striking precision. Both teams expected distant supernovae to appear brighter than they would in a universe expanding at constant speed. If expansion was slowing down, distant galaxies wouldn't have traveled as far as expected, making their supernovae appear closer and brighter. Instead, they found the opposite. Supernovae that exploded when the universe was 2/3 its current size appeared 20 to 25% fainter than predicted. This meant they were farther away than expected, which could only happen if cosmic expansion had been slower in the past and was now speeding up. The implications were staggering. For expansion to accelerate, some form of energy with negative pressure must dominate the universe. This concept defies everyday experience. Ordinary matter and radiation have positive pressure. They resist compression. When you squeeze a gas, it pushes back. Dark energy has negative pressure, meaning it pushes space apart rather than pulling it together. As the universe expands, ordinary matter becomes more diluted, like drops of ink in an expanding balloon. But dark energy maintains nearly constant density, making its repulsive effect increasingly dominant. The measurements revealed that this mysterious dark energy comprises approximately 69.4% of everything that exists. Dark matter, detectable only through gravity, makes up about 27%. All the atoms, molecules, stars, and galaxies we can see account for just 5% of the cosmic energy budget. We live in a universe dominated by two invisible components we barely understand. It's as if we discovered that 95% of our house was made of materials we'd never seen or touched. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for this discovery. Yet their triumph immediately created physics' greatest mystery. How could something so dominant remain completely undetected? What could possibly drive the universe apart with such relentless force? The discovery was like finding that invisible hands were stretching the fabric of reality itself. Dark energy presents theoretical physics with an embarrassing failure. When scientists try to calculate what should cause cosmic acceleration, they get an answer that's wrong by a factor of 10 to the 120th power. To put this in perspective, if you guessed the number of atoms in the observable universe and were off by this same factor, your estimate would exceed the number of atoms in 10 to the 110th power copies of the entire observable universe. Imagine trying to measure the width of a proton and being off by the distance to the nearest galaxy. That's still a smaller error than physics makes with dark energy. The calculation seems straightforward. Quantum mechanics tells us that empty space isn't truly empty. Virtual particle pairs constantly appear and disappear throughout the vacuum, creating quantum fluctuations that should contribute energy to space itself. These ghostly particles pop into existence for impossibly brief moments before annihilating each other. This vacuum energy should act exactly like dark energy, pushing space apart through negative pressure. The problem is the numbers. Quantum field theory predicts vacuum energy density of approximately 10 to the 113th joules per cubic meter. Observations of cosmic acceleration suggest dark energy has a density of about 5 times 10 to the negative 10th joules per cubic meter. The theoretical prediction exceeds observation by 10 to the 123. This discrepancy is so vast that physicists call it the worst prediction in physics. It's like predicting a mouse weighs as much as a galaxy. Multiple attempts to resolve this catastrophic mismatch have failed spectacularly. Some theories propose that unknown symmetries cancel most of the vacuum energy, leaving only a tiny residual amount. Supersymmetry, a hypothetical relationship between different types of particles, could in principle provide such cancellation. In supersymmetric theories, every known particle has a superpartner with opposite properties that could cancel out vacuum energy contributions. However, decades of searching at particle accelerators have found no evidence for supersymmetry at the energy scales where it was expected to appear. Another possibility involves the swampland conjecture from string theory. This suggests that most mathematically consistent quantum field theories cannot actually be realized in a universe with quantum gravity. Perhaps the vacuum energy we calculate using standard quantum field theory simply doesn't exist in the real world. But this approach basically admits defeat. It says our best theories of fundamental physics break down when applied to the largest scales. The cosmological constant problem connects to an equally puzzling coincidence. Dark energy and dark matter have comparable densities today, but they evolved completely differently over cosmic history. 13 billion years ago, dark matter dominated while dark energy was negligible. 5 billion years ago, their densities became approximately equal. Today, dark energy slightly dominates. Why do we happen to observe the universe during the brief cosmic epoch when these two mysterious components have similar influence? It's like arriving at a party exactly when two unrelated events happen simultaneously. Some scientists invoke the anthropic principle. This is the idea that we observe this particular cosmic epoch because it's the only time when conditions allow complex structures like galaxies, stars, and life to exist. In the far future, dark energy will dominate so completely that galaxy formation becomes impossible. In the distant past, the universe was too hot and dense for complex chemistry. Perhaps conscious observers can only emerge during the narrow window when dark energy and matter densities are comparable. This explanation feels unsatisfying to many physicists. It suggests that one of the universe's most fundamental properties cannot be calculated from first principles, but must simply be accepted as an environmental condition necessary for our existence. It's like explaining why water boils at 100 degrees by saying that's the only temperature at which we could exist to observe it. Recent theoretical work has explored whether dark energy might not be constant but instead evolving over time. If dark energy represents a dynamic field rather than a fixed property of space, its strength could change as the universe ages. Some models propose that dark energy was weaker in the past and is gradually strengthening. Others suggest it might be weakening or oscillating. Each possibility leads to different predictions for the universe's ultimate fate. Recent measurements have provided increasingly precise values of the universe's current expansion rate, deepening cosmology's greatest crisis. The H0 Distance Network collaboration announced that space expands at 73.50 kilometers per second per megaparsec, with an uncertainty of just 0.81. This represents precision better than 1%. This should have been a triumph. Instead, it made the Hubble tension impossible to ignore. The problem lies in the mismatch between different ways of measuring cosmic expansion. When astronomers observe the cosmic microwave background radiation left over from when the universe first became transparent 380,000 years after the Big Bang, they can calculate what the current expansion rate should be. This ancient light carries the fossilized imprint of sound waves that traveled through the primordial plasma. This method yields approximately 67 to 68 kilometers per second per megaparsec. The 8% difference between these measurements might seem small, but it's statistically impossible to explain as random error. It's like two perfectly calibrated rulers giving different measurements for the same object. Multiple independent techniques now confirm both values. The early universe measurement comes from the Planck satellite's exquisite maps of temperature fluctuations in the cosmic microwave background, combined with our best understanding of how the universe evolved from that early epoch to today. The late universe measurement builds a distance ladder using nearby stars called Cepheid variables to calibrate the brightness of Type 1a supernovae at increasing distances. The H0DN collaboration specifically designed their 2026 analysis to rule out single systematic errors as explanations for the tension. They combined observations from multiple space telescopes and ground-based facilities, cross-checking distance measurements using different techniques. Their conclusion was stark. This work effectively rules out explanations of the Hubble tension that rely on a single overlooked error in local distance measurements. If the tension is real, as the growing body of evidence suggests, it may point to new physics beyond the standard cosmological model. Several exotic explanations have been proposed. Early dark energy models suggest that dark energy was present and significant much earlier in cosmic history than the standard model assumes. By changing how the universe expanded in its first few 100,000 years, early dark energy could alter the calibration between early and late universe measurements. Calculations show this approach can reduce the Hubble tension from a 7 sigma disagreement to 2 or 3 sigma. Another theoretical framework called JCDM cosmology proposes that dark energy density scales with the expansion rate itself, varying as the universe evolves. This model yields a Hubble constant of approximately 66.95 kilometers per second per megaparsec, agreeing with early universe observations while achieving improved fits to late-time data. The approach preserves compatibility with cosmic microwave background observations by maintaining the acoustic horizon scale that determines the size of temperature fluctuations. Gravitational wave observations offer a completely independent path to resolving the tension. When neutron stars or black holes spiral into each other, they produce gravitational waves that carry information about their distance. These ripples in space-time itself provide a direct measurement of cosmic distances without any intermediate steps. Unlike optical observations, gravitational wave distance measurements don't depend on the traditional distance ladder or assumptions about early universe physics. As more gravitational wave sources are detected, they may definitively determine whether the Hubble tension reflects systematic errors in optical measurements or genuine new physics. The stakes are enormous. If the tension is real, it suggests our standard model of cosmology, which successfully explains the cosmic microwave background, galaxy formation, and element abundances, is fundamentally incomplete. New physics might involve previously unknown particles, modifications to general relativity on cosmic scales, or exotic interactions between dark matter and dark energy that we haven't considered. The most ambitious dark energy experiment ever built has detected something unexpected. The Dark Energy Spectroscopic Instrument, mounted on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona, has mapped the positions of 47 million galaxies and quasars. This represents 38% more than originally planned. This three-dimensional map of the cosmos, spanning 11 billion years of cosmic history, reveals hints that dark energy itself might be evolving. DESI works by measuring baryon acoustic oscillations. These are regular patterns in how galaxies cluster together that were imprinted by sound waves in the early universe. Think of them as fossilized echoes from when the cosmos was a hot, dense plasma. These patterns provide a standard ruler that allows astronomers to measure cosmic distances and expansion rates at different epochs. By observing how this ruler appears stretched or compressed at various distances, DESI can track how dark energy's influence has changed over time. The first major surprise came from the sheer scope of DESI's observations. The instrument uses 5,000 fiber optic cables to simultaneously collect light from thousands of galaxies, creating the largest three-dimensional map of the universe ever compiled. Each galaxy's spectrum reveals its distance and the expansion rate of space when its light was emitted. Combined with Type 1a supernova observations, this data provides unprecedented precision for measuring dark energy's behavior across cosmic history. Analysis of DESI data released throughout 2024 and 2025 suggests that dark energy may be weakening over time. When combined with supernova measurements, the observations provide evidence for dynamical dark energy at confidence levels ranging from 2.5 to 3.9 sigma. These represent deviations from the standard model at these significance levels. If confirmed, this would fundamentally challenge the assumption that dark energy remains constant. Particularly intriguing is evidence for what researchers call the quantum scenario, where dark energy's equation of state parameter crosses the boundary of W equals -1. In the standard model, dark energy has W exactly equal to -1, corresponding to Einstein's cosmological constant. Values greater than -1 indicate weaker dark energy, while values less than -1 suggest stronger repulsion. DESI data hints that this parameter may have evolved from above -1 in the early universe to below -1 today, or vice versa. Nathalie Palanca de la Bruyere, a scientist at Berkeley Lab working with DESI, stated, "The weakening acceleration observed by DESI can no longer be explained with a cosmological constant. This could be the most interesting discovery in cosmology since that of dark energy itself. Such evolution would require dark energy to be a dynamic field rather than a fixed property of space-time." However, caution is warranted. The evidence for evolving dark energy, while suggestive, remains at levels that permit large uncertainty. Statistical fluctuations or systematic effects in the data could potentially explain the observed patterns. The significance levels of 2.5 to 3.9 sigma fall short of the 5 sigma standard typically required to claim a definitive discovery in physics. DESI continues collecting data, and full analyses of the complete 5-year program are expected in the coming years. These results will either strengthen the case for dynamical dark energy or reveal that the current hints result from statistical noise. Additional surveys, including the Vera Rubin Observatory's Legacy Survey of Space and Time, will provide independent tests of dark energy evolution using different techniques. The implications of evolving dark energy extend far beyond academic cosmology. If dark energy is weakening, the universe's accelerated expansion might eventually slow or even reverse, leading to a big crunch where everything collapses back together. If dark energy is strengthening, acceleration could become so extreme that it overcomes all other forces, ultimately tearing apart galaxies, stars, and even atoms in a Big Rip scenario. Recent theoretical work has explored how quantum gravity effects might drive such evolution. Recent theoretical studies have explored how quantum deformation parameters from the generalized uncertainty principle could couple to cosmic expansion, potentially driving super-accelerated evolution leading to Big Rip behavior even without a cosmological constant. Their calculations showed that positive deformation parameters accelerate the ripping process, while negative values could cause different regions of spacetime to separate and evolve differently. If dark energy continues strengthening over cosmic time, the universe faces a catastrophic end unlike anything in science fiction. The Big Rip scenario describes a future where accelerating expansion becomes so extreme that it overcomes every force holding matter together, ultimately destroying the fabric of spacetime itself. The mechanism operates through runaway acceleration. As dark energy grows stronger, its repulsive effect overwhelms the gravitational attraction binding cosmic structures. First, galaxy clusters fragment as expansion pulls their member galaxies apart. These vast collections of hundreds of galaxies, held together by dark matter's gravitational web, begin to dissolve. Calculations suggest this could happen in approximately 22 billion years if dark energy strengthens at the rate some models predict. Next, individual galaxies lose their ability to hold together. The Milky Way's spiral arms would stretch and distort as stars get stripped away from galactic centers and scattered into the growing voids between galaxy remnants. Solar systems follow, with planets torn from their orbits around dying stars. Earth would drift alone through empty space, no longer bound to the sun. Eventually, even stellar remnants like white dwarfs and neutron stars succumb to the relentless stretching of space. The final stages become truly bizarre. As acceleration intensifies, it begins competing with the fundamental forces that bind atoms together. The electromagnetic force holding electrons to nuclei weakens relative to the expansion force. Atoms stretch like taffy until their electron clouds can no longer remain bound to their nuclei. Matter as we know it ceases to exist, replaced by a soup of disconnected particles. In the ultimate phase, even atomic nuclei face destruction. The strong nuclear force, which binds protons and neutrons together, represents the most powerful interaction in nature. It's the force that powers stars and creates the elements. Yet if expansion accelerates sufficiently, the stretching of space-time can overcome even this fundamental force. Protons and neutrons get pulled apart, leaving only elementary particles scattered through an empty, expanding void. Finally, space-time itself tears apart at what physicists call a singularity. This is a point where physical quantities become infinite, and the mathematical description of reality breaks down. Time effectively ends, not with the heat death predicted by classical thermodynamics, but with the complete destruction of the geometric structure that allows time and space to exist. Recent calculations suggest this nightmare scenario might occur even without dark energy in the traditional sense. Theoretical studies have shown that quantum gravity effects described by the generalized uncertainty principle could drive Big Rip behavior through coupling between quantum deformation parameters and cosmic expansion. Their work demonstrated that positive quantum deformation values lead to super-accelerated evolution culminating in finite-time singularities, while negative values cause spacetime regions to separate, with one contracting and the other freezing rather than ripping apart. The timeline for such destruction depends critically on how rapidly dark energy strengthens. Conservative estimates based on current observations suggest the Big Rip, if it occurs at all, lies at least 50 billion years in the future. More extreme models could compress this timeline to as little as 20 billion years. This is still far longer than the current age of the universe, but short enough to affect the long-term evolution of galaxies and stars. However, the Big Rip remains speculative. Current observations provide only weak evidence that dark energy is strengthening rather than remaining constant or weakening. Desi's hints of evolving dark energy could equally well indicate weakening acceleration, which would lead to very different cosmic futures. If dark energy weakens sufficiently, expansion could eventually slow and reverse, causing a big crunch where the universe collapses back to a singularity similar to the Big Bang. Alternative scenarios include cyclic cosmologies where expansion and contraction alternate over vast timescales, or heat death where expansion continues at a steady rate until all stars burn out and black holes evaporate, leaving only elementary particles in a cold, empty universe. The key point is that dark energy's behavior over cosmic time remains unknown. Whether it stays constant, strengthens, weakens, or oscillates will determine not just the universe's ultimate fate, but the future evolution of every structure within it. Current and planned observations may resolve this question within the next decade, revealing whether we live in a cosmos destined for violent destruction or gradual decay. Dark energy represents the deepest mystery in modern science. Something invisible and poorly understood dominates the cosmos, driving apart the very fabric of space-time with a force that defies our best theories. Einstein's greatest blunder has become the universe's greatest puzzle. The numbers are staggering and humbling. Dark energy comprises 69.4% of everything that exists, yet quantum physics predicts it should be 10 to the 120th power times stronger than observed. The Hubble tension suggests our standard model of cosmology may be fundamentally wrong. Desi's observations hint that dark energy itself might be evolving, potentially changing the universe's ultimate destiny. We stand at a crossroads in cosmological research. Within the next few years, Desi's complete dataset, combined with observations from the Vera Rubin Observatory and gravitational wave detectors, may finally reveal whether dark energy remains constant or evolves over time. These measurements will determine if we face heat death, big crunch, or big rip scenarios for the cosmos. The answer will reshape our understanding of physics and our place in the universe. The implications extend far beyond academic curiosity. Understanding dark energy could open new physics beyond general relativity and quantum mechanics. It might reveal connections between the quantum vacuum and cosmic scale phenomena, or demonstrate that space-time itself possesses properties we never suspected. The solution could change technology in ways we can't yet imagine. For now, we remain inhabitants of a universe dominated by the unknown. Every second, dark energy pushes space apart by amounts we can measure but cannot explain. The force that may ultimately determine the fate of every atom in existence remains as mysterious today as when it was discovered nearly 3 decades ago. Two teams of astronomers shattered our understanding of reality, expecting to find the universe slowing down. Instead, they found something pushing everything apart. That something still holds the universe in its invisible grip, accelerating us all toward an uncertain future.